Hi everybody, welcome to Linear Algebra Chapter 6 with me. Today we're going to talk about vector on vector multiplication. And the reason we're going to do that is we haven't really done that yet. We did matrix and matrix, and so in that sense we kind of talked about it, but we haven't done vector and vector. And today we're going to answer the question, can we find a way to multiply vectors together so that it's geometrically useful? We have geometrically useful things. For instance, when we add our vectors together, we can do this tail to tail and then find the resulting vector. We can do scalar multiplication. And so if you have a vector, it gets scaled out even further or maybe shorter if the scalar is a small number. And then even matrix multiplication can have a geometric interpretation, because when you have the eigenvalue problem stuff, A is acting like a scalar. It scales V. So these all have nice geometric meanings. What about for vector times vector? Can we do that? Not really, technically, ish. Because, like, dimension-wise. So we're going to do U and V both in Rn. That means if we try and multiply U and V, we're going to have, let's see, n rows, one column, an n by n, or an n by 1 and an n by 1. But remember, when you're multiplying two matrices, which vectors are matrices, those inner dimensions need to match. And here they do not. So we're not really multiplying vectors together, but we're going to say math's kind of all made up, and so we're going to do it anyway. So first definition, we're going to define inner product. We've got two vectors, and the inner product is just the sum of component-wise multiplication. So you just take V1 and U1, V2 and U2, all the way down to the end, and you add them up together. So note, this is often called the dot product. This is from Calc 3, so you have indeed seen it before. And dot product is a special inner product. As you go further into math, you're going to get more generalized definitions for inner product, and dot product is just a very specific example. All right, important thing to notice is dot products take two vectors and maps them to a scalar, right? Because this is just, it's not vector times vector anymore. This is just one component times another component, and that's a scalar. And so we're adding a bunch of scalars together. So shockingly, we end up with a scalar. And then I kind of lied. I said we were making things up. We're not being quite so cavalier. This is related to the matrix product that we already know. See, if you do V transpose times U, I think I put the transpose on the right one. Let's see. So U is an n by 1. That means the transpose would be a 1 by n. The dimensions are now good to go. They match. And then when you look at the result, this is going to be a 1 by 1, which is a scalar. So just like we had. So we're still related to the matrix multiplication that we did before, but we don't really want to bother with talking about transposes and stuff. I guess we got lazy. Another thing I'm going to point out is that I'm not going to write U and V right next to each other, because that would imply that I'm trying to do normal matrix multiplication. And so they get this special dot that's in the middle. You have to put them there, otherwise you're talking about something else. Okay, so let's do an example. Let's see this in action real quick. We've got V dot u. Then we take the first entries, so 1 times 4. We take the second entries, 2 times 5, plus the third entries, 3 times 2. Notice, unlike determinants, there is no alternation of signs or anything. We just add them all up, keep those straight. And then that's 4 plus 10 plus 6, so that's 20. Okay, properties of inner products. We've defined something new. We've got a new operation, so of course we've got to talk about, can you flip it back and forth? Does it matter what order it's in? Can you distribute? Yes, 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 to all of them. So these three, probably not too shocking. You can prove any of these component-wise, by which I mean same song and dance that we've been doing. So that would be like V1, U1 plus all the way out as per the definition. But then like V1 and U1, we can swap the order of those guys. So U1, V1, UN, Vn. And so that would be U dot V. So unlike matrix multiplication, these guys can switch back and forth. Okay, so that would be number 1. And then I'm gonna leave 4 and 5 for you guys to do on like homework or worksheets or something. Okay, now we're gonna get into like length, norm, magnitude. It's all the same thing. These are all the same word that basically just says, how long is my vector? It is defined by this guy right here. So notice there is a square root in there. And we say it has norm squared right here if we want to like stop talking about the square root basically. Okay. So you've actually seen this before. This is probably reaching back almost as far as I can into math to like talk about inner products. This is Pythagorean's theorem, I promise. Let's look at it. Let's consider what happens in R2. Here we go. Here is our vector. I'm going to say it's just A and B. So then that means we would have like, this is A, this is B, like that. So we could put B on that side. So then let's do Pythagorean's theorem. Remember, Pythagorean's theorem is we look at C and we're like, so what is the hypotenuse of this triangle? AKA, what is the length of our vector? And we say C squared equals A squared plus B squared. Okay, but that is just equal to, we'll say, V dot V, right? Because if you go component-wise, you do A times A plus B times B. So that's just V dot V, which is the norm squared. So we can say that C equals the square root of V dot V, where I am not bothering with the plus or minus because when we talk about length, you don't talk about, oh, that's negative inches tall. Not a thing. But there we go. In 2D, it's just Pythagorean's theorem. So Pythagorean's theorem is an inner product. Crowd goes wild. Okay. So another thing that we know, like fact-wise about vectors, like in 2D especially, we know that if we multiply, say, this vector right here by a scalar, here, I'll write down the words. So, multiplying a vector by, I already used C. We're going to use D. By D makes it D times longer. So if I multiplied it by 2, your vector would get twice as long. That's what I'm trying to say. So what does that look like in math? Like, how can I use our new and improved definition of inner product and norms in order to prove this? Well, we're going to start with the length of c times our vector, and then hopefully we'll get that it's, or I'm using d. And hopefully we'll end up with this, because this is the length of our vector, and this would be like saying d times longer. So let's see if we can string these together. So definition of the inner product. Thankfully, it's still sitting on this page, so I can just write square root dv dot dv. There we go. And then I can feel free to move those d's out to the front by inner product properties. And then we can just square root each of these individually. Not a problem. Okay, so then do these match up? And we're like, well, that's definitely the definition of that right there. But does the square root of d squared go to the absolute value of d? And yes, for all intents and purposes here, because we're talking about positive length. So if I wanted to like multiply my vector by -2, the length would still expand by 2 times. It is 2 times bigger, not -2 times bigger. Sure, the direction and stuff change, those things change, but we're just talking about length. That's all positive, and that's why we've got absolute values sitting on there. So yes, those steps match up. In which case, we are done QED. All right. So next definition, we've got a vector is called a unit vector if the length, right here, if the length of u is 1. Now let's say we have a non-zero vector and its length isn't necessarily 1. We say that the unit vector in the direction of v is given by this guy here. So you just take your vector and you divide by the magnitude of that vector, because then you're going to have a total length of 1. I will go through it real quick just to make sure we're comfortable with it. That would be like doing this. Okay, so this is just a scalar right here. Comes in handy. Our previous fact, we can just move that to the front with an absolute value sign. And then we just have to worry about this. But oh wait, we are doing the absolute value of a positive number right here. So that's just 1 over v times v. Those are just normal numbers, and we know 1 over a number times a number is indeed going to be 1. Okay. So we say, we have vocab for this too. We say we are normalizing a vector v by going from original v to the unit vector version of it. So that's called normalizing a vector. And let's go ahead, let's try and normalize a vector or two. So let's say we have v is equal to 1, 1. I don't know. I always thought it was kind of weird. Like, it makes sense that the length of the vector isn't 1, but inside, I want it to be 1, guys. I really do. But, like, here you go. That's what vector v looks like. So if we normalize it, that means we're going to need the length, which is going to be 1 squared plus 1 squared, which is just the square root of 2. So then the unit vector version is going to be 1 over root 2 times 1, 1, which is equal to 1 over root 2, 1 over root 2. Okay. Hint, that should look like, you know, unit circle stuff. Okay. Here's not unit circle, just so that we can see different example. How about -3, 0, 4? We're going to take the magnitude of W. We're going to say that's going to be 9 plus 16. So that's square root of 25 equals 5. So then the unit vector version is going to be 1/5 of the original vector. So we will say that is -3/5, 0, 4/5. There we go. We have normalized some vectors. Okay. So next we've talked about like length of vectors. What's another thing that kind of goes with like length? Distance. So we're going to talk about distance between vectors. So distance is going to be given by just subtracting the two vectors and taking the magnitude. You're like, why does that work? Let's go ahead and see why that works in, once again, 2D. We love 2D. So if we do that, you're going to get, we'll say vector x, and then we have vector y. So that means we would have x minus y like this. And so the length of the vector here would be the distance between our vectors, because we're only interested in like the distance of the tips. Okay. Let's calculate this out. What do we get? If we do distance between x and y for some general vectors in R2, that's just this. And then, well, we know what x minus y is. We're going to write it like this. Just a general x1 entry and a general y1 entry. There we go. So then when we take the magnitude, we're going to have first component squared minus second component squared. We're going to square root it. Question. Does this look familiar? I hope it does. It's distance formula. You may not have used it in a long time, but remember finding the distance between 2 points? Well, that would be like saying, oh, this point here and this point here, which would be the tip of our vectors. So really, the distance between u and v is just distance formula, but generalized for vectors that aren't necessarily in R2. But this brings us to something interesting. Remember, distance formula kind of worked because of like perpendicular triangle things. Right triangle, sorry. Right triangle things. And so like, what if we have like this? Remember, distance theorem was kind of related to like Pythagorean's theorem. Or distance formula was related to Pythagorean's theorem. So what if we have like this isosceles? We have like theta, c, and ab. Could we find this distance c? And the answer was yes. That was law of cosines. So distance formula was really like a specific law of cosines. So let's remember law of cosines, because this is going to give us some cool stuff. Law of cosines. Here, let me draw our picture back like this. Remember that beautiful formula right there. Let's translate this over to using like u and v instead with vectors. So we've got vector u vector v, and then this would be like u minus v. Okay, so let's plug this into law of cosines. Then we're going to have u minus v, so the length of that vector would be like this c over here. So that's going to be equal to, and then a would be like the length of our u vector. So if we plug this all in, oh, got to square those. That's important. Okay. So there we go. We plugged it into law of cosines. I'm also going to do something else. We can also do another way. Let's go at it from the dot product way, because we know things about dot products. So this would just be u minus v, no square root because I'm squaring it. Okay, and then just like normal FOIL, dot product is going to work just fine. So like that, minus 2 uv plus v dot v. And then we know what u dot u is. That's going to be just u squared like that. And then same thing for v. Oh, I dropped my dot product. Bad. There we go. So now notice that this part matches this part matches this part, and so the only thing that's left over is like that guy and that guy. So those guys have to be the same then. So that's going to give us negative 2u dot v is equal to negative 2 u v cosine theta. And then we can simplify that a little bit. Let's get rid of that ugly 2. Sorry, 2, you're actually a very wonderful number. You are not ugly. Okay. There we go. Does this look familiar? This is from Calc 3. You guys would have had this as another way to find dot products. It's back. So you've seen this before. I keep saying, do you remember this? If you're not saying yes and you're like, oh my goodness, I'm supposed to remember all these things, it's fine. I have the memory of a goldfish. I didn't remember any of this. I was just like, wow, I'm seeing this for the first time. But anyway. Okay. So this is a new way to think of dot product, even though today's version of dot product was probably also a little bit new. But interesting fact, just to notice for funsies, we know something very specific about u and v. We know they're going to equal 0 if theta is equal to pi over 2, because cosine of theta, or cosine of pi over 2, would be 0. So that's kind of cool. Let's get into this theta thing, though, because we haven't really defined him yet, and we are blooming mathematicians. We want definitions for everything. So here we go. We have two formal vectors, v and u, and the angle between v and u is going to be the angle theta. That is not going to be, we're not going to let them be negative, and we're not going to let them be bigger than 180 degrees. So we're restricting ourselves to just this part, such that we get cosine of theta equals the dot product of the two over the magnitude of both, which, I don't know, that felt very arbitrary to me when I took this class, and nobody pointed out, just divide both sides by those guys, and Now you have it. Okay. So I've pointed it out. Hopefully it feels less arbitrary. Why do we care? Because we really just care about this next definition. Two vectors are orthogonal if their dot product is 0, which should make all the sense in the world because we're like, oh yeah, like 90 degrees, like in R2, that would be perpendicular lines. So you're just talking about perpendicular stuff. Like, yes, I am, but we're in linear algebra, so we say orthogonal now because we're fancy. Okay, so where does this leave us now? Okay, we're going to do an example where we calculate an angle just real quick for V and U. We're going to need 3 things. We're going to need the magnitude of V, the magnitude of U, and the dot product of VU. So let's go ahead and calculate those just so that we feel good about crunching these numbers. Nope. 4 squared is not going to be 4, it's going to be 16. Okay, so this is going to be the square root of 64, which is 8, which is great. Magnitude of U is going to be equal to square root of 1 plus 64 plus 225 plus 49. And then you add that all up and you get 339, which I really feel like should be an exact square, but it's not. So then we've got U, and we've got dot V. So that's going to be -3 times 1 plus 7 times -8 plus 4 times 15 plus 0. Okay, so that's -3 minus 56 plus 60, which is 1, which that one worked out really nicely. Yay! So then cosine theta equals 1 over the top of 8 times the square root of 339. And then this is not on your unit circle. You do not need to know what this is off the top of your head. But I do expect you to be able to plug this into a calculator and interpret that. I personally found the information more helpful in degrees, because in radians it was something like 1 point something, and I was like, I don't know what that means. But then you flip it to degrees and you're like, oh, 89 degrees, I know what that is. That's almost perpendicular. So almost perpendicular, but they weren't. All right, so now that we've got all this stuff about perpendicular, let's like really lean into this, orthogonal. Let's really lean into this orthogonal thing. Okay, so let V be a subspace, then the orthogonal complement to V, which we even denote it with the little perpendicular symbol, is the set of all vectors U such that you're going to get U and V are orthogonal for each other for every single V in big V. So what we should think, big picture, V perp is all the vectors that are orthogonal to all of the V vectors. For example, so A, let's think about, we'll say this is V. It is the span of one vector, 1, 1. So that would be the line going through the origin with slope 1. His orthogonal complement is going to be this guy, so V perp, and he is going to be the span of everybody with like a negative slope, so 1, -1, like that. Yes, you could have done -1, 1 instead, because they are multiples of each other. It's fine. Okay, Another easy like visual example for us is plane through the origin. So we're going to do, let's see. Let's do this plane. Like that. So plane through the origin. Then I can spell origin. There we go. So what would be perpendicular to that? Do you guys remember Calc 3? Reach back. Calc 3, perpendicular to a plane. Normal vector. So this guy. So then V is going to equal, or V, not that, V perp equals the normal vector, basically. Or all linear combinations of it. Span of the normal vector. There we go. Okay, so those are two quick visual examples of what the orthogonal complement to V would be. Notice that, let's see, we already said that V had to be a subspace. We said we couldn't talk about the orthogonal complement unless V was a subspace. But notice that V perp, these are also subspaces. We already know that span is subspaces. Is this a thing? Yes, yes it is a thing. If V is a subspace, then its orthogonal complement is also a subspace in the exact same space. So this would be a great time to pause and try and work through that because you guys know what subspaces are, and so hopefully you guys can verify this on your own. Okay. So, first question. Is 0 in V perp? Well, we're going to start with a V that is in V, and we're going to figure out if 0 would be orthogonal to it. So then the 0 vector dotted with this vector is just going to be 0. So then we can say that the 0 vector is orthogonal to V, and this works for all V's in V. We didn't pick a special V, we just said, oh, just any V, and so it'll work for all of them. That's what this symbol right here means, by the way. I think I've talked about this symbol for all. Yeah. Okay. So then 0 is in V perp. So even if you couldn't get this started, pause now. Try and do the addition one by yourself. Okay. So now we're going to assume that we have two vectors that are in V perp, and we want to know if they're going to be, if their sum is going to be in V perp. How did we figure that out? Well, we've got to multiply it by something in V. And we're going to say, and V is in V. There we go. So what happens if we multiply the sum of these two guys, or dot product, my bad, not multiply. Well, we know dot products distribute. So U dot V plus W dot V. But wait, U is in the orthogonal complement, so that's just a 0. W is in the orthogonal complement, so that's a 0. So there we go, we got 0, we're good. So U plus W is indeed in V perp. Last one. If you haven't paused yet, please pause. Do this one by yourself. Let U be in V perp. And C is going to be some scalar. So then CU, we want that guy to be in V perp, which means we need to dot him with some V that is in V. Okay. So again, using properties of dot products, U is in V, or U is in V perp. So that's just a 0. So that's 0. So then, yes, the dot product was 0, so they are orthogonal. So there we go. CU was indeed in V. And again, I didn't say anything special about the vector V, and so I might as well have tested it against everything in V, because V, the vector, was arbitrary. All right, we're winding down. We're getting close. So, question, how can we test if a vector U is in V perp? Like, beyond this, like, what if we have a more specific example? Like, do we go through and just try it with every single vector? Absolutely not. That's impossible, because if we check it for every V in a subspace, that's too many vectors. That's infinitely many, because you have infinitely many linear combinations. So that's not the answer. So theorem, what we're going to do is, in order to figure out if U is in V perp, we just need to check if it is orthogonal to a basis of V. Any basis will do. So if we just check it against the basis vectors, that's good enough. We know it's going to be perpendicular to everything. Why? You should try and do this on your own too. This is another good one, very accessible. So proof. Forward direction. Very easy, it's like 2 steps. But just to model some good proof writing habits, I'm going to say that we are assuming U is in V perp, because we are starting with this side and we want to get this side. So WTS, if you don't know, means want to show, and it is the lazy man's way of writing that. Okay. I think we're going to be okay. So want to show U dot V1 are all going to be 0. Okay. So if it is in V perp, by definition, U dot V equals 0 for all V in V. But the basis of V is also in V. So the basis elements, so V1 all the way up to VP are in V. So, I should make that look like a capital V. So U dot V1 don't be bad, never forget your vector symbols. It is important. Okay. So there you go. We're done. We got where we wanted. Next, we have the, let's see, so that was the forward direction. Backwards direction. Once again, let's model some good proof writing. We want to start with V1 up to VP is a basis of V, and C1, nope, not C1, my bad, UV1 these guys are all equal to 0. What we want to show that this is going to be 0 for every v. But how do we do that if all we know is it works for the basis vectors? Well, we think about what it means to be a basis vector. What does it mean to be a basis vector? It means this guy is going to be a linear combination of the basis vectors. There we go. So we don't care about like equals 0 linearly independent. No, we just care about it is a basis, therefore any vector in V is a linear combination of our basis vectors. So let's run with that. Let's try and do u dot v. Let's see if we can get 0. That would be the same thing as u dot this linear combo. And then we can distribute that. There. Can even factor out that c when we distribute. There we go. Okay. But we know that u dot v1 is 0. We know that u dot all of those guys is 0 because that was the assumption right there. So that's just a big fat 0. So, yep, u is orthogonal to v for some random v that we do not know. So then u is in v perp. Done. Yay! So that's it. We wanted to find a way to multiply vectors together that was going to be geometrically informative, and goodness, are we informed now? We're like 40 minutes later. We are very informed. There are a lot of things we discovered. There were a lot of things that we were actually already privy to because we knew about distance formula, we knew about Pythagorean's theorem. Turns out it's an inner product. Lots of cool stuff, lots of cool things that it related to that you guys already knew. But anyway, I will talk to you guys later. Enjoy. Have a good one.